Welcome to Week 2 Reading the Textbook. Chapter 4, Our Regenerative World. Climate. Climatic factors determine everything we do or place on a site we are designing. They influence every decision. If you mix up your climatic applications, your system will fail. A Cavendish banana plantation cannot grow in the cold temperate zones, for instance. This section will acquaint you with what you need to know for each major climate zone and for some minor climate zones. There are also the local climatic and orientational factors that strongly influence design specifics on site. The slope, watershed orientation, distance from large bodies of water, elevation, wind, sun path, and fire dangers. Beyond strictly environmental factors of climate, there is also the social climate and our own emotional, physical, and mental climate. These factors can sometimes influence what we do on a site as much or more than ecological factors. Climatic factors are very complex and influenced by both regular and irregular factors like longer-term cycles of the sun, moon, and earth, atmospheric factors like volcanoes and pollution, and extraterrestrial factors like meteors and solar flares. There is an accepted general consensus in the scientific community that there is an observable rise in more violent and erratic weather patterns like flood, hurricane, and storms, as well as an unprecedented rise in global temperatures. It is best to plan for variable weather and temperature patterns by designing with diversity. Climate change is already here and disrupting the patterns that we've come to rely upon. We can mitigate these extremes and begin to restore our atmospheric systems to normalcy through large-scale land restoration projects. Understanding the historical highs and lows, the extremes over time of rain, wind, temperature, flood, migration, etc. is vital. This gives us a clear list of things to expect or to investigate for their absence. For example, the largest historical rain event is used to design all roads, dams, catchment sills, and swales. We need to know how much rain the swales or dams should be able to hold. We can source libraries, elderly members of the community, town hall records, local historians, or even the internet. The information is usually available in your area through one of those channels. Broad climatic zones. The broad zones below are meant to help guide us rather than restrict us. We may find our site is a mix of subtropical and Mediterranean temperate. Arid and desert zones are found throughout all climates as well. Looking at the climate map, we can readily see that these zones are not evenly distributed, with the most obvious imbalance being the northern hemisphere containing most of the world's temperate climate landmass. We can also spot our area and its color and search out our climate analogs all over the world. Tropics. At or close to the equator with temps above 18 Celsius or 64 Fahrenheit year-round. Subtropics. Extends away from the equator to the tropics of Cancer and Capricorn with temperatures never below 0 Celsius or 32 Fahrenheit. Temperate. Mediterranean, warm, cool, cold. With temperatures below 0 Celsius and 32 Fahrenheit in winter and above 10 Celsius and 50 degrees Fahrenheit in summer, this zone extends from the tropics to the Arctic and Antarctic circles. Polar. Below 10 degrees Celsius and 50 degrees Fahrenheit year-round, dominated by ice and snow. Arid, 50 centimeters or 19.5 inches or less of rain a year. Desert, 25 centimeters or 10 inches or less of rain a year. Precipitation. Every climate has fluctuations and cycles that affect its precipitation. No average is reliably true in nature, only a generalized rule of thumb. We should always harvest rain even in areas with regular precipitation because of seasonal, man-made, or cyclical droughts. Researching drought, intensity, or duration can help us be prepared and design with these specifics in mind. We should look into the extremes of precipitation to understand how much rain we could get in a 50 or 100-year storm event. This will help us design our dams, swales, homes, and gardens. Understanding the pressure on our dam walls is critical to protecting our homes, buildings, gardens, animals, and others from flood damage or worse. Consulting professionals when constructing dams, buildings, and anything that could be potentially hazardous is always wise. The distribution of the precipitation over the course of the year is important to understand. In some areas, they get most of their rain in only a few days. Intensity of rains can also increase flooding, especially during the longer cycle storms like a 50 or 100-year storm. The intensity of precipitation influences how we design our roofs, roads, swales, dams, and more. Measuring the water that falls is a simple and easy way to calculate how much moisture an area receives, but it omits condensation's contribution, which is often difficult to calculate. In this area, do your best and always accommodate for a margin of error. Build things a bit big. Buy a larger storage tank for the rainwater, etc. Be prepared for excess precipitation, especially as groundwater and ground ice continue to end up in the oceans and the skies. Some areas are naturally drier. The constant upwelling of evaporation at the equator leads to rising columns of warm moisture in a spiraling cycle that generates predictable atmospheric patterns that are influenced by the shifting tilt of the planet. These patterns are called Hadley cells. These atmospheric patterns tend to create areas of shifting droughts and belts of brittle climates across the globe, 15 to 30 degrees from the equator. Desert belts across the world, the Sahara, the American Southwest, parts of Australia and Peru, the Middle East, are all influenced by this effect. In areas with only coastal fog, precipitation doesn't reach far enough into the land's interior, as is the case with the Namib Desert. The fog is caused by cold ocean currents meeting the shoreline and leads to a rich maritime ecology, but a desert inland beyond the coastal fog's reach. Orographic Effect. There are specific effects related to rises in elevation that are observable. Air flows cool, condensing moisture as they rise over mountains and hills. This increases condensation, which increases cloud formation and all forms of precipitation. In areas with a prevailing wind, storms tend to drop the majority of their moisture on the windy side and very little on the sheltered side because of the rise in altitude condensing the moisture in the airflows. This is called a rain shadow and is easily recognizable. The eastern side of the Sierra Nevada mountain range in California is visibly drier than the west side when seen from the satellite or witnessed firsthand. The jet stream flows west to east. In addition, as you move up in altitude, it is the equivalent of moving up through progressively colder climate zones, even at the equator. The sun path and day length are still those of the equator, however, so transferring foods and seeds from a colder temperate zone to a mountainous tropical region and vice versa doesn't work out perfectly. The seeds are all photoperiodic specific to their original bioregion. The adaptation can be made, but takes technique, patience, and work. Cyclonic Effect. When hot and cold media meet, especially in the atmosphere, they form cyclones of rising hot air and falling cold air. This can be seen in the form of a hurricane or tornado. This is also occurring in liquids that are stirred into a whirlpool. The water is being pulled up from the bottom as it is being pulled down from the top. The Archimedes screw pump is an excellent example of cyclonic effect being applied to serve human needs. Convection Effect. Hot air rises from the desert or ocean into the upper atmosphere where it cools. Thinking this way illustrates quickly how we can use this effect to diffuse, concentrate, or channel hot or cold air by design. Joel Saladin, the regenerative farmer, has portable chicken houses that have openings up top and down low to allow for hot air to rise and for cool air to be pulled in. This creates a consistent flow of air which cools and creates the air which both the chickens and the farm in turns benefit from. Dew. Dews are commonly caused by clear nights, rapid heat loss, and atmospheric moisture settling over coasts and hills. Dew coats plants and surfaces with moisture. As the sun rises, its warmth begins to evaporate the dew. A significant amount of moisture is soaked into the soil, consumed by organisms, and absorbed by plants. These processes are difficult to accurately measure as the functions are stacked, happening in real time and outside of a laboratory. We've yet to design machines as efficient, sophisticated, and reliable as anything found in natural systems and cycles. Distillation. Water vapor rises from the ground into the atmosphere but can collect on all the leaf surfaces as it passes. If we drip line irrigate, even below the surface, we can rest assured that the vapor will distill on the plants above the surface. Having a closed canopy, having multiple layers in our food forest or agricultural system, and using shade, we can recapture moisture repeatedly as it cycles. Fog. Often carrying more moisture than dew, fog can provide enough moisture to support life, even on islands without bodies of water or with low rainfall. Fog is a critical source of water that can be harvested carefully using trees in water catchment hardscapes like stone cisterns, or in more recent times, mesh fencing with gutters at their bases that drain into cisterns or water tanks. Radiation ground fog. In hollows or gullies where it is naturally shaded or cooler, fogs and frosts form. Advection fog. When warm air from the sea meets cold winds from inland, they form a thick fog that many a port city is often shrouded in. Upslope fog. Warm, humid air streams rise and condense as the air cools, part of the orographic effect. Condensation. When warm air cools, it drops the moisture it was holding onto surfaces. Water vapor can collect onto surfaces from fog or even clear air when there is a cooling of the night air. This moisture is very difficult to calculate since it is vapor collecting on all exposed plant parts and at the same time being absorbed. In design, a common condensation trap is to arrange stones in a circle around a tree along the tree's drip line, or strategically place small piles of stones to condense moisture. Often worms attracted by this coolness will begin working around the soil below these stones. Radiation. Solar radiation. Solar radiation is the sun's energy, which is mostly filtered by the atmosphere and found in excess primarily at the poles and high altitudes. The atmosphere filters the sun's energy perfectly for life systems to use. It is thinner higher up and thicker closer to sea level. From plants to animals, we all benefit from the stable temperature ranges the atmosphere and sun's energy together create. The sun's light is necessary for human health as well for the well-being of most ecosystems, plants, and animals. The tilting of our planet throughout the year creates wax and wane to the solar radiation. This pulsing effect of more and less solar radiation is part of the most basic pattern for all life on Earth. It directs the flowering of plants and the germination of seed. It powers our weather, seasons, and ocean systems. Solar radiation is a source of all energy on Earth. Even the Earth's core is powered by the sun's energy. Color. The darker the color, the more absorption of light, greater radiation release of heat, while the lighter the color, the more reflection and less absorption and later release of heat. We can observe this when we enter a black versus a white car that has been parked in the summer sun for several hours. If there is a black interior, it might even be too hot to touch. A home built in the desert that attracts heat with a dark coloring will store heat and give it off during the night, while a home that is painted white will block heat and therefore not absorb and give off as much heat. Often greenhouses in cold temperate climates use black water barrels against the back wall of the greenhouse to store solar energy from the daytime and radiate it back out overnight. Albedo effect and absorption. Albedo is the effect of light reflecting off natural surfaces and plants. This can be the winter snowpack atop Yosemite's majestic half dome or a white wall on a house. Light that is absorbed is turned into heat that is conducted and radiated outward. We can use this understanding to filter, reflect, absorb, focus, or transmit the solar energy we receive naturally. Heat. Convection. A low-grade heat that travels in liquids or gases such as air, wind, or water. The equivalent to this in the home would be an electric heater which blows hot air. It is an inefficient way of heating a home by focusing on heating the air instead of the objects themselves. Conduction. An intermediate grade heat that travels solid to solid or fluid to fluid by contact. This can be the most effective way to transfer heat. This is the fundamental basis of the rocket mass heater. It conducts the heat through a mass. Radiation. High-grade heat that heats solids and liquids but affects air very little. Thermosiphon. Applying heat to the bottom of a loop or chimney causes the air in the loop or chimney to move, allowing for the heat to rise using the convection principle. We can use this principle to draw out heat from an area as well. A solar pump or solar chimney is a tall black pipe that extends much higher than the house. It collects heat in the sun all day, drawing out heat from the house with the intensity of the heat at the top of the pipe. It creates a suction by forcing the air in the pipe to rise, similar to a rocket stove. We can also fan hot air into cool sinks like a sunken path in a greenhouse. This air exchange is healthy for plants as well. Glass houses attached to homes can also serve as thermosiphons to warm a home in a cold climate, as seen in the diagram. Heat factors. Latitude and season. Distance from the equator and time of year. Slope angle. Facing the sun straight on or perpendicularly, we absorb the most solar radiation. The greater the angle of the slope, the more indirect light, the less we absorb. Sun-facing slopes receive more solar radiation than slopes that face away from the sun. Air clarity. The amount of dust, ice, vapor, or smoke in the air affects the capacity for heat to be absorbed or released. A cloud of volcanic ash can have a cooling effect by blocking the solar radiation. Advection. Winds bring cooler or warmer air to areas of different temperature. Warm air that enters cooler regions creates condensation, as it does in forests. The thermal belt. A strategy for many temperate climates in areas that are not too hot is to build home sites on sun-facing slopes below hilltops and above the valleys and plains. Cold night air leaves quickly in direct early sun, while the soil retains the sun's heat longer, extending warmth into the night. Frost and cold nighttime air lakes form in the valleys and gorges. Ridges and hilltops are windy. On hilltops, water has to be pumped up to homes with windbreaks and extra insulation needed to keep houses warm. To save energy and time, plan to build in the thermal belt or its equivalent on your property. Frost. When air rapidly cools over a still spot, frost can occur. To prevent frost, have steep hollows or steep-sided holes that are thinner than they are tall. The inverse creates frost. Large open fields or holes with open sides that invite the wind. In design, holes can be dug with steep sides to prevent frost falling on sensitive plants. Or clearings in forest can be narrow to prevent frost, half as wide as tall, and retain warmth. Insulation. Insulation. Earth, brick, stone, fiber, straw bale, cob, or concrete can prevent heat from being lost by blocking conduction into the ground or radiation into the air. The thickness of straw bale home walls provides more insulation than most conventional homes. This extra insulation lowers heating bills dramatically by greatly preventing conduction and radiation loss. Heat absorption by plants. High biomass plants like trees can hold and radiate captured solar radiation throughout the cooler parts of the day and night. However, this effect varies depending on the season and the tree variety. Large, dark evergreens trap and exude heat, while white birch trees reflect the heat. Trees with more leaves and branches absorb more heat than trees with fewer leaves. The opposite is also true. The larger the tree, the greater the shelter and shade it provides, which is producing a cooling effect. It all depends on the tree, time of day, and the season. Water, earth, and stone. Water, earth, and stone store heat well. We can capture heat from the sun and water, earth, and stone and use it to warm cold areas or focus the heat into a microclimate. We can also reflect and block solar radiation or allow light further into the home as well. We can even insulate the thermal masses to slow conduction and radiation loss. Wind. Winds have regular patterns and pulses that vary according to their location on the globe, the season, and local effects such as topography. On slopes, hot winds rise uphill during the day and cool winds fall downhill during the night. Using windbreaks and wind funnels of trees and/or berms, designers can block, lessen, or increase wind on a site, thereby increasing or decreasing the amount of warmth held in that site. In areas of intense wind, all design considerations come after initial windbreak design. Crops and animals are also affected by wind intensity. Winds can carry salt, sand, nutrients, pollutants, organisms, and other particles from one area to another, which can have negative or positive effects on plant and animal systems. Many coastal, island, subtropical, and exposed slope regions are subject to winds, cooling, and erosive effects. In some areas, hardy, wind-tolerant species arranged in a windbreak to shelter a garden from sand or salt are the only way to grow food. Windbreak is essential in these areas where heat or light-related transpiration is already occurring. The addition of wind may well kill or stymie the growth of the plant. Windbreaks create still, protected microclimates in which more tender plants can thrive. Tree flagging. Though winds can be seasonally or daily bimodal, we can determine the prevailing wind by the shape of trees and specifically by the branch crown in relation to trunk placement. See picture. The wind literally pushes the tree crown away from the trunk to varying degrees, which tells you the severity of the wind in that area. You can tell a lot about a site from the wind and water patterns that are already in place before a design even begins. When we are to thin an area, we should spend time examining the trees first. Identify the trees you wish to cut and make sure you aren't creating a wind tunnel or a frost pocket. Use the natural patterns to influence your design, whether it be the final design, thinning a forest, or building a house. Look for indicators like tree flagging to tell you the story of that place. Building windbreak. Research hardy native species that are commonly found in local high wind areas, including all layers from grasses to canopy trees. From this plant list, choose the most beneficial polyculture to the system, both from an ecological and human usage perspective. Use the trees, and if feasible, fencing, earthworks, or even stone to create turbulence and push the air upward while slowing the infiltrating air. In areas where establishment is difficult, layers of wind-hardy trees may be needed to create a fully protected inner zone. Some areas may need a salt-resistant layer first to withstand the desiccating sea breezes or desert sandstorms. In high wind areas, regular windbreaks within cropping systems may be needed to keep the winds at bay.